Hello everyone. In this video we are going to talk about some basics of state space control and also controllability and observability. So you know that you can show a dynamic systems as long as it's linear and time invariant. You can show it with a transfer function, and here we need one output and one input, so the ratio of the output Laplace to the input Laplace, assuming zero initial condition, is called a transfer function. Or you can show it with what in the state space, where you have the system dynamics x dot equal ax plus bu, a bunch of first order differential equations, and the output, which is cx times plus du, and u is the input signal or signals, and x are the vectors. X is the vector of the states. X are the states of the system, and y is the output. So you might say, why would you use this state space over this transfer function? Well, for systems that has single input, single output, there is not a big difference in terms of showing the dynamics of the system. But when the system gets multiple input, multiple output, MIMO, as opposed to SISO, which is single input, single output, you have multiple inputs, multiple outputs. So this U has more than one number in it, and the same with Y. Then you're going to have a matrix of transfer functions, not a single one. And instead of that matrix of several of these polynomials, basically, in a more compact format, you can show the whole system with just four fundamental matrices, A, B, C, and D, where the name of A is the system matrix or the state matrix, and that's the most important matrix, which determines basically the stability of the system. B is called the input matrix, which relates the input effect or shows the input effects on the dynamics of the system. C is the output matrix, which shows the relation between the states and the output, and D is called the feed-forward matrix, which shows direct relation between U and Y, input and output. So this is in general more compact. It allows much easier control, as we'll see in the next lecture, called pole placement or pole assignment for MIMO systems, and it shows many other advantages and many other analysis. It makes it a lot easier, like controllability, observability, observers, and a lot more. So in general, in systems with multiple input, multiple outputs, this state space is much more preferred compared to the Laplace plus. These differential equations are mostly first order, and they're easier to solve and also easier to simulate. Now, if you want to go from a transfer function to state space or vice versa, in MATLAB there are two commands, SS to TF and TF to SS. So state space to transfer function and the other one, which you can use. And one thing I want you to know, and I guess I explained it in one of my previous videos on a state space, is going from state space to the going from transfer function to the state space is not unique. There could be so many different ways that you can go from state space to transfer function to state space, and that depends on what is this vector x that you decide. Depends on what states you select. Depending on that x, you will get different matrices A, B, C, D. So this is not unique. But going from state space to transfer function is unique. And the formula for that, you can very simply show that it is CSI minus A inverse B plus D, okay? And that is not really hard to show. If you want, I can very fast show you that, and all you need to do is basically to take Laplace from the two sides of this. So if you take Laplace from this top one, here you get S x, or S times I times x, and x here is capital X, right? It's the Laplace of x, And on that side, you get A times X of S plus B times U of S. And this bottom one will be Y of S equals C times X of S, and then plus D times U of S. And what you need to do is to eliminate X between these two equations. So from the top one, you take this A times X of S to the other side, so you will get basically Si minus A times X equals B times U. So you multiply both sides by Si minus A inverse, right? So it gives this here to be your X, right? X is going to be CSI minus A inverse times B. So that is your X, right? In terms of U, and you plug it here, so it's going to be C times that plus D times, and since that X has a U in it and this other term has a U, you can factor it out. So the result is Y is going to be C times that matrix, CSI minus A inverse B, plus D, the whole thing times U. So if you divide both sides by U, your transfer function is going to be this guy. And again, it's unique. And in MATLAB, as I said, there is a command for that. So let me show you that part here. If we go to MATLAB, for this example, a specific example, I'm gonna go ahead and show you how to go from the transfer function to the state space, right? So you need to define the transfer function. So you say the transfer function system is equal to the transfer function of, then you pass the numerator and denominator. And in our case, numerator is 10, 10, denominator is 1, 6, 5, 10, right? So 10 and 10, and then 1, 6, 5, and 10. So this is the transfer function. As you can see, we want to basically go to the state space. Now for the state space command, if I say A and B and C and D equals transfer function to state space, and I pass this sys to it, you're going to get an error. This command transfer function does not need an input that is already in the Laplace domain like that. What it needs is the numerator and what? Denominator. Look here, if I do it, it says, hey, not enough input arguments, because again, it needs the numerator and denominator instead of the whole system. So you have to pass these guys to it. And now, look, it says A is negative 5, negative 10, 1, 0, 0, 0, 1, 0. Now, if you look here, look, this is different. This is kind of like the rows are swapped, basically. And that's probably because the order of the variables that you chose in the state vector is opposite of what MATLAB has chosen. Okay, and if you look at C, it's like 1, 0, 0. Here it's 0, 10, 10. Okay, so the output probably looks different too, and B is 1, 0, 0. And you can see B here is different, D is 0, and here is 0. Okay, so you see that in this example that I got from the book Ogata, there is one basically representation. And if you look at MATLAB gave you another representation in this status. As I said, going from the state space to going from transfer function to state space is not unique. But if I give this A, B, and C and D, and I ask for the transfer function, right? So if I use the command state space to TF, and I pass this A, B, C, and D to it, right? This command should give you the same transfer function. Again, this does not return the whole system. It returns a numerator and what? A denominator. So you have to use it like that. And if you do, look, 0, 0, 10, 10, 1, 6, 5, and 10, which is exactly that. Now, if I use that matrix here, that's for A, that for B, that for C, that for D, I still get this guy back. Okay, so it's unique. Now, As I said, matrix A is very important. It's called the system matrix. The eigenvalue of this matrix are the characteristic roots of the transfer function, and so they determine the system's stability. So in this case, if I go with matrix A and find the eigenvalues of that, let's see what they are. So that's matrix A, remember, in this case. And if I say what are the eigenvalues of A, so it says one is negative 5.41 and the two others are two complex conjugate, right? But as you can see, the real part of all of them are negative. That means the system is stable. Now, if you remember, the denominator was what? The denominator was 1, 6, 5, and 10. So I can pass that denominator to the command roots. And do you see here? These are the roots of the denominator, which are the poles of the system, and or the roots of the characteristic equation. And these are the eigenvalues of matrix A, and they are the same thing, right? So if you want to look at the stability of the system in the state space, you're not going to solve for the roots of a polynomial, right? You're going to look at what? Look at the eigenvalues of the state matrix, and that will tell you whether the system is stable or not. Good. Another thing I need to tell you before I go to controllability and observability is state transition matrix. What is that? So this equation, this dynamic equation, as I said, is a first order ODE. And so since A and B, if we assume them to be constant matrices, and they are not depending on time because the system is linear time invariant, then we can solve this in general. So the solution of that is going to be this e to the at times the initial condition plus this convolution here, which is involving the e to the at with some delay tau times bu of tau d of tau. So this is the change in the state as a result of the input, and this is the change in the state from the initial condition. And you see in both of them, this e to the at appears. So this e to the at, where A is the system matrix, this e to the at, which is a time function, this is called state transition matrix. And you see, if there is no input to the system, basically this tells us how you go from initial condition to any time points, including the final values. And one simple way to get this e to the at is, this is the Laplace inverse of Si minus A inverse, okay? That is going to be what? E to the at. There are other ways to use the Cayley-Hamilton theorem and the other methods of expanding it based on determinants for calculating e to the at. But most of the times it's really a good idea to use this inverse Laplace, and it can help find e to the at quite a bit faster. So if you define S in MATLAB as symbolic, and then get the inverse of Si minus A, it is going to give you basically this, right? And now you need to find the inverse of these elements, okay? The Laplace inverse of these elements. So if you can find, for example, Laplace inverse of this, let's see if MATLAB can do that. And okay. Now you see MATLAB cannot do an amazing job, unfortunately, on that, and probably the reason is that two of these roots are complex numbers. Okay, so MATLAB is not doing a beautiful job on that, and yeah, if you do partial fraction expansion on this, then you can easily find the inverse Laplace of this. Okay, but again, since MATLAB is dealing with complex roots here, it might have a hard time finding the inverse Laplace of that. So if you do partial fraction in MATLAB, or just you do it by yourself and then using the tables of Laplace, you can easily find the inverse of these. So now let's talk about two topics that are the main thing for me to explain in this video. One is controllability, the other one is observability. We say a system is controllable at time t0. T0 could be 0, for example, or any time. That's the initial time that the dynamics of the system starts. If the system can be transferred from the initial state, x at t0, to any other state, arbitrary x, over or in a finite time interval using unconstrained control inputs. Well, what does that mean? Means I want the system to start at some initial state and go to any other state. So you want to start at x of t0, and after some time t, okay, you end up at some x desired, and this t here, or t minus t0, is a limited time, so it doesn't take forever to do that. You are able to do that with some signal u that you pass to the system as the control signal, and this u could be unconstrained. Okay, so you're not going to put any constraint on u, but you should be able to find a signal u that allows you to go from this initial state to what? To this desirable final state in a limited amount of time. If you can do that, then we say the system is controllable, right? So I can control it in any way I want. I can make it go to any state that I want. Then we say the system is controllable. And to determine the controllability, you can use this augmented matrix and see if the rank of this matrix is full rank, rank n. If the rank of this matrix is full rank, then the system is controllable. Well, the components of this matrix is B, the input matrix, A times B, A squared times B, all the way to n to the n minus 1 times B, where n is the order of the system, right? So for this system where A was 3, n was 3, so you just go to what? To A squared B. And so this matrix is going to be n by n, or 3 by 3, this augmented matrix. And then we'll look at the rank of this matrix, see if it's rank 3 or not. If it's full rank, then we say the system is controllable. So if I want to try that over here, right? Remember, this is A, this is B. So I form a matrix, which is B, and then what? A times B, and then it is what? A squared times B. Okay, so it should give you this 3 by 3 matrix, and if I run the command rank on this, you see the rank is full rank, rank 3. So this system is definitely controllable. Okay, the system, you can take it from any initial state to any desired state at any time in a limited time interval. Okay, so that's as simple as it gets for checking controllability. And you might say, well, could you explain that a little bit more, like, or could you show me a system that is not controllable, right? Could you show me a system that is not controllable? And I say, well, let's take a look. For example, this is my A matrix, right? Now, if I go ahead and have a system in which, and this is like your B, right? Like that. So if I expand these equations, what do I get? Let me just expand these equations so I can explain them better to you. So if I expand these 3 equations, what does that mean? It means x1 dot equals what? Equals x2. x2 dot, if you look, equals x plus 10 times u, and x3 dot is equal to negative 10x1, negative 5x2, negative 6x3, and negative 50 times u. So now you clearly see if I choose a U, that U is going to affect the dynamics of X3. It is going to change how X3 is changing versus time. So U is affecting this equation. So it is going to affect the second equation as well, because it is affecting X3 indirectly through the bottom equation, and it's also directly affecting the dynamics of X2. So it has effect, direct and indirect, on X2. And then when you control how X2 is changing, then since X2 is what? Is equal to the derivative of X1, therefore you can control how X1 is changing versus time. Right? So you see, whether direct or indirect or both, this U has effect on the dynamics of all three variables. So it can change the overall vector X, which is X1, X2, X3. Right? Now you might say, well, what happened if I did not have this 10? Right? So if this 10 was 0, correct? If that 10 was 0, would that system still be what? Still be controllable? And for that, first, let's go ahead and look at it in MATLAB and then come back. So here I'm going to use that A matrix and that B matrix instead of the one that MATLAB gave me. Okay, so these are these guys, and I get that matrix again, and you can look at the rank of it, which is 3. So you see the original system is controllable. Now what I do, I come and change this matrix B. I change this 10 to 0. Form the matrix again and get the rank of that. And look, again, the rank is 3. Still, the system is controllable, even if what? If this 10 becomes a 0. Why? Because although this time U is not directly affecting X2, but indirectly by controlling X3, still can affect X2. So if this is 0, still I'm controllable. Okay, now you might ask, could you do something to this A and B matrix and make it uncontrollable? Well, let's see what we can do. For example, let's say here, if I bring that negative 50 to here, up here, so I make this guy negative 50. Okay, right? So x1 dot becomes x2 minus negative 50 times u. So u is directly affecting x1. Okay. Also, u is affecting what? U is affecting x2. Right? Now, what I need is get rid of these guys. And maybe that one. Well, that one I already got rid of, so make it 0. And here, get rid of these two, so make these two 0. So your x3 dot just going to be negative 6x3. Is this system going to be controllable? No. Why? Because you can directly change x1 and x2, but the effect of that x1 and x2 is not showing itself in x3 because I made these guys 0, and u is not directly showing up in x3 dynamics. So you see, the equation of x3 has no effect whatsoever from u, and the solution of x3 here is simply whatever it was at time 0 times e to the negative 6t. There is no u in it. Okay? And so this mode x3, this state x3, is not controllable by the input, so we say the system is not controllable. So here, this is what I'm going to do. I'm going to go back to A and get rid of these two elements, make them 0, go to B, right, and then B, I make this guy negative 50, make this guy 0. Right, and now I form my augmented matrix, and clearly you can see I have a row of 0. So the rank of this guy is definitely 2. And so this system is not controllable. Do you see? So that's the meaning of controllability. Means your input or inputs can directly or indirectly show up in your dynamic equations and affect your states. Then I can say the system is controllable. Okay, finally, observability. What does observability mean? Observability of system at time t0 is if it's possible to determine the state of the system at that point, which is x at t0, by measuring the output or outputs over a finite time interval. So remember, your system is what? Your system is like a box that the input goes in, or the inputs, and the output comes out, right? Like this. And inside this system, there are these state variables. So observability means if I have a sensor, right, to measure this for me, from those measurements of the sensors, I can guess what, or have some, not just guess, I mean some real scientific calculated values for X. So if I know Y, I can get what? I can get the values of X, right? At any point, all I need is to calculate the values of X at any point is to look at the Y over a short amount of interval and guess the states of the system at any point. That is called observability. For that, we need this augmented matrix, where C is there, and then C times A squared, all the way times C times A to the n minus 1. This matrix has a bigger dimension, nm times n instead of n by n. Still, the rank of it at max could be n. So if this matrix is full rank or rank n, we say the system is what? Observable. Okay? So let's go ahead and again look at this physical system again that we had before we change all of these numbers, right? Before changing all of these numbers, let's go back to the original system and see if this system is what? Observable. So I go back to the original A, which was this, I guess, go to original B, which is this. And I now need a C. We really need C right now. And C, let's use 1, 0, 0. And now we need to form the augmented matrix, which again is what? C and then CA and CA squared. And here, since n is 2, the maximum you go down is CA squared. So you go like C, and then below that you get C times A, and below that you get C times A square, like this. Okay, and this is your matrix. Clearly you see it's rank 3 already. It's the identity matrix, right? It's rank 3, so this system is absolutely observable. Okay, this system is absolutely observable. And again, you might say, how could you explain that based on these equations? Well, let's take a look here. What is the output? In this case, your output is x1. So clearly, if you observe the output, it means you know what x1 is. But if you know x1, could you also guess x2 and x3? Well, yes. Why? Because if I know x1, I can take derivative of that numerically, and that means I know now what? x2. You're right. If you know x1, simple numerical derivation, and that means what? That means x2, right? Let's look at the equations. Here. Right? There we go. And if I know x2, does it mean I can also find x3? Well, look. Yes. Why? Because look at x3. x3 is derivative of x2. Now, of course, I also need to know the input signal, but input signal is always a given signal, right? You know U already. What you need to sense is y. U is under your control. You can always have it. You can always measure it. So U is not an unknown. U, you know it. And you just need to add 10 U's to it. And that gives you what? That basically is going to minus 10 times U actually. Right? Because x3 is x2 dot minus 10U. So you take derivative of that, subtract 10U, and that means what? x3. So you see, knowledge of x1 derivative is x2, knowledge of x2 derivative minus 10U that you know is going to give you x3. That means you can have all three values. And that means the system is what? Observable. Now you might say, well, if you swapped some numbers here, you made this guy 1, you made this guy 0, would the system still be observable, right? Well, first let's check it in MATLAB and see if we change C to be like this, would it still be observable? So here, look at this, and clearly this guy is still rank what? Rank 3. So the answer is yes. If I change it to the last element, what about this? Would this also do the job? You still see that what? Let's look at the rank. Still 3. So yes, you can still do it. So you might say, is there any way that I can make the system not be observable? Again, yes, you can do that. And how? Well, let's just go back to the 1 and 0, but this time we want to manipulate some of these equations. So we disconnect the relation between output, input, and one of the states, so that one state is not accessible or not being, not affecting the output at all. Okay, so you define output in a way that one state is not really showing itself in it. So for that, what I need to do is something like this. I take care of these two elements, make them 0. So x3 dot is just like that. Okay, it's still affected by the input. Okay, so the system's still controllable. But now I say what? I say y equals x3. Okay? I say y equals x3. Let's see what happens. So here, this is what I'm gonna do. Look. I change C to 0, 0, 1, and I change my A to this. Here, I made these two 0. Now, I form my observability matrix. Remember, it was C and C times A, and what? C times A squared, right? This is it, and clearly, if you look at the rank of this, is what? Yes, you're right. The rank of this is 1. So clearly 2 modes are not observable. 2 modes are not observable, not just 1. 2 state variables cannot be observed, not just 1. Because the rank is, instead of 3 to 1. And you might say, where are they? What are they? Well, clearly you see y is x3. So observing y means I know x3. But what about x2 and x1? If I know x3, doesn't it mean that I know x2 dot? No. Because if I know x3 and I know 10u, it means I know x dot. And knowing x dot is not the same as what? Knowing x. Remember last time, if I know x1, it means I know x1 dot, which is x2. But here you are going backwards. If you know the derivative of something, does it mean that you know that something? No. Because here you need to integrate. And integration needs a history. Okay? And you don't always have the data. Okay, so numerical derivation can be done, but not numerical integration, because you're losing some of the history behind that time point. And so if you know the derivative of x2 dot, numerically you cannot find x2, right? That is a mathematical, it needs further mathematical explanation, but I'm sure you can look it up. So if I give you some numbers, right, and I ask you to take derivatives, you can do that by forward, backward, or central derivative. But if I give you a bunch of numbers and I say, give me that x2, okay, as a function of time or at a specific point, you might not be able to do that, because the integral under the x2 dot is going to give you change in x2. So when I look at this area under the curve, right, this guy, when I do that area under the curve, that is the change in x2. And if I don't know the x2 at the end, I cannot subtract this from to get the x2 at the beginning. So in this case, mode x2 is not accessible, and when x2 is not accessible, guess what? x1 is not going to be accessible as well. So none of them can be accessible, none of them could be not accessible, I mean observable, and so both of these are out of observations. So that's why the rank of that matrix was 1. So hopefully I could clarify for you with some explanation what observability means and what controllability means. And this is for this video. It's already quite a bit long, so I'll see you in the next lecture, where I show you how to do a regularization in state space using pole placement. Thank you for your attention, and I'll see you in the next lecture.